Hello, today we'll talk about plane strain, plane stress and plane strain problems. These are the methods of converting the three-dimensional equations to two-dimensional ones so that we can solve them easily. And in many problems, this assumption or this two-dimensionalization is possible, but not in all. So we have to be careful where we apply this. So let's go and look at the formulations. In fact, we have discussed this earlier, that there are 15 unknown variables in elasticity problems. And you may remember there are 6 stress components, 6 strain components, and 3 displacement components. And we have also got 15 equations, compatibility equation, equations of equilibrium, and continuity equations. So we have got 15 unknowns and 15 equations. And we also have boundary conditions. So along with that, we can solve them easily. But in many cases, this solution becomes complicated because of the number of variables. So there are many methods of solving them. And one of the methods is to convert these three-dimensional problems into two-dimensional one. And in that, there are two methods. One is plane stress formulations, and other is plane strain formulation. As I said earlier, that these formulations cannot be used anywhere. There are certain conditions which we have to comply with before we use these formulations. In fact, these are basically assumptions. And under certain conditions, these assumptions are valid. In certain other conditions, these assumptions are not valid. So let's look at the plane stress problem. In plane stress problem, we consider a domain which is bounded by two parallel planes. In fact, this can be very easily taken as a thin plate, where the thickness of the plate is much smaller compared to the other dimensions, so that we can assume that the stresses in one of the directions, say the z directions, are 0. And equation A shows that. We can assume under this condition that sigma z, tau xz, tau yz is equal to 0. This indicates that we cannot apply a stress in the z direction, and it is also physically difficult if you consider a thin plate where we want to apply a stress or traction or body forces in the z direction. So we consider basically a stress field which is independent of z. This is important to remember. Stress field independent of z. So we go ahead and see what would be the other formulations, because in order to solve the unknowns, we need to use 15 equations and in different sets. So let's go ahead and see. If we consider the stress tensor under plane stress condition, then it simply becomes a 2 by 2 matrix, because I have shown this, I have shown the three-dimensional stress matrix on the right-hand side. And if you make the sigma z, tau xz and tau yz, then you have only this part of the matrix, and we have here a 2 by 2 matrix. So things become very simple here. So if we now look at this and go back to the procedure that we followed in finding out the principal stresses, then what we did is to write down the characteristics equation. And the characteristics equation I have shown here, you can see that in 3 dimensions, the characteristic equation looks like this. But then if we again let the stresses in the z direction be 0, then this characteristics equation reduced to this form on the left hand side, where it is simply sigma x minus sigma. Sigma is the characteristics value actually, tau xy, and then tau xy sigma y minus sigma, and then another column matrix of Lm, and that will be equal to 0. N is not there because it's only 2 dimensional. So now, if we remember that when we found out the eigenvalue of this matrix, of this characteristic equation, what we did is to let the non-trivial part of this equation to 0. So the determinant of the non-trivial part of the equation is simply this. If you take the determinant of this matrix, non-trivial part, then you have got sigma square minus sigma x plus sigma y into sigma minus sigma x sigma y minus tau xy square equal to 0. Now this is a much simpler equation compared to the equation that we had for the 3D. Now I have shown the 3D equation here just for comparison. If you look at this equation, this is the equation that we use for a 3D characteristics equation. So let's look at this and let us put the stresses in the z direction equal to 0. So sigma z is 0, sigma y, sigma z, then this component is also 0. Then tau yz and tau xz is also 0. This is a multiplication of sigma x, sigma y, sigma z. So this whole thing is 0. Then this is tau xy, tau yz, tau zx. That is also 0. And this is also 0 because there is zx, yz component. And there is also zx component. And only this term also contains sigma z. So this whole thing, the last term in this equation becomes 0. So we are left with only the first 4 terms. In the 4 terms, all of them has got sigma. So if sigma is not equal to 0, we can cancel out sigma, and we get this equation. So if you look at this equation carefully and apply the plane stress conditions, that is sigma z, tau xz, tau yz equal to 0, then you will come down to this. And this also comes down, you can get this also by taking the determinant of the non-trivial part of this equation. So we are left with a very simple quadratic equation, and if we solve them, then we can get our very well-known principal stress equation, that is sigma x plus sigma y by 2 plus minus root over sigma x minus sigma y by 2 square plus tau xy square. So you see, by considering a plane stress condition, we convert the problem to a very simpler one in 2D, and then the whole thing becomes much simpler and we get our well-known principal stress conditions. And that is given in equation number C. Okay, I think there's nothing great in this. This I think we can understand well. So let's go to the next page. Now we also need to consider the stress-strain relation, and that will be by Hooke's law. So I have shown the Hooke's law here. I have shown the Hooke's law here for 3D, and on the left-hand side, I have shown the Hooke's law when we apply the plane stress state. That means where sigma z, tau xz, tau yz 0. So if you do that, the first line becomes epsilon x equal to 1 by E sigma x minus mu sigma y, because there is no sigma z. Epsilon y is 1 by E sigma y minus sigma mu sigma x. Again, there is no sigma z. And epsilon z, you see sigma z 0 does not mean epsilon z is 0. So epsilon z will be there, and that is equal to minus, because sigma z is not there, so it is minus mu by E sigma x plus sigma y, and that will be equal to, we can write it in terms of epsilon x and epsilon y, but this is probably not needed in this case. So epsilon x, epsilon z becomes minus mu by E sigma x plus sigma y. Now epsilon xy will be there. Epsilon xy will be simply tau xy by g. And g, if we write in terms of E, it will look like this. So epsilon xy is 2 1 plus mu by E, that is the inverse of g and tau xy. Okay, that's simple. And then epsilon xz and yz, they are 0. That is the condition of the plane stress. So if we apply the plane stress in Hooke's law, it becomes a simple 4 equations which eliminates sigma z, sigma x, tau xy and tau yz, and tau xz and tau yz. Now here, the one thing you have to remember, that our condition for plane stress is sigma z, tau xz, tau yz is equal to 0. Since tau xz and tau yz are related to epsilon xy and epsilon xz and epsilon yz by simply by g, epsilon xz and epsilon yz will also be 0. Because look at here, what is epsilon yz? Epsilon yz is tau yz by g, and epsilon xz, I have written here gamma, but we have taken here same as epsilon xz. Epsilon xz is tau xz by g. So then epsilon xz and epsilon yz are 0. But epsilon z is not 0. This you have to remember. And that is why we are getting an expression for epsilon z. So in plane stress, sigma z, tau xz, tau yz 0. That also means epsilon xz, epsilon yz are 0, but epsilon z is not 0. Okay, so that is the Hooke's law part of it. Now let's go to the strain displacement conditions. We know that the strain displacement are given in terms of displacements. And we all know this, we have discussed this many times. Epsilon x is del u by del x, epsilon y is del v by del y, epsilon z will be there as we said before, and that will be equal to del w by del z. Epsilon xy will be again shear strain del u by del y plus del v by del x. This we have seen before. But epsilon yz is del v by del z plus del w by del y is 0, because this is strain in the z direction. Epsilon xz is also similarly 0, which is del u by del z plus del w by del x equal to 0. So when we look at the strain displacement, we have got only 4 equations: epsilon x, epsilon y, epsilon z, and epsilon xy. Again, here you have to remember that epsilon z is not 0, because in the plane stress condition, sigma z is 0, but epsilon z is not 0. Okay? Let's go to the next set of equations, and they are the equations of equilibrium. I have written the equations of equilibrium on the right hand side in the 3D, and equations of equilibrium on the left hand side for static equilibrium. That means in the full form of the state of equilibrium equations, we have got mass into acceleration on the right hand side. But if we take static equilibrium, this part will not be there. So we have got 0 on the right hand side. And also we put sigma z 0, tau xz 0, tau yz 0, and any variation with z is also 0. If we do that, you will see, then look at the first line, del sigma x by del x, that we have here, plus del tau xy by del y, that we have here, but del tau xz by del z will be 0. So that is not there. Plus x, the body force, is equal to static equilibrium, right hand side is 0. Next line, we have got tau xy or yx or xy by del tau xy by del x plus del sigma y by del y plus del yz plus del z. This term will be 0 because tau yz is 0, plus y, capital Y is the body force, and the right hand side is as usual not there because this is the mass into acceleration, which is not applicable for static equilibrium. So we have got here del tau xy by del x, del sigma y by del y plus y is equal to 0. So we have got a very simple form of the equilibrium equation which contains only 2 equations. Now, in addition to this, we also have to look at the compatibility equation. And as we remember, in the compatibility equation, there are 6 equations. And if you go through this one by one, you will see all the equations will be satisfied except the first one. Satisfied if you apply sigma z, epsilon sigma z, tau xz, tau yz equal to 0, which means epsilon xz, epsilon yz is equal to 0, and any variation with z is also 0. So let us look at the second equation. In the second equation, we have got del square epsilon y by del z square. So this is the variation with z, that is 0. Then we have got del square epsilon z by del y square. So epsilon z is 0. And on the right hand side, we have got del square epsilon yz by del y del z. In fact, del square epsilon z by del y square may not be 0. But then this equation becomes, if it is everything else is 0, then this equation becomes futile. So I think this we do not consider. Next equation we've got del square epsilon z by del xs square plus del square epsilon x by del z square is equal to del square epsilon zx by del x del z. So this is also satisfied and we don't need to take this into account. Similarly, if you go through the other three equations and apply that epsilon xz, epsilon yz, and variation with in the z direction or del by del z is 0, then you will see all these equations are satisfied except the first one. So we write that the only applicable compatibility equation is del square epsilon x by del y square plus del square epsilon y by del x square is equal to 2 del square epsilon xy by del x del y. So we have got a number of equations for the plane stress state of stress, and there are A, B, C, D, E, F, G. And these equations are sufficient to solve plane stress problem. We look at a simple problem to understand this. Consider a plane stress state express for a plane stress state. Express the stresses in terms of strain using Hooke's law. From Hooke's law for plane stress, we have seen that we have got only three equations. Epsilon x equal to 1 by E sigma x minus mu sigma y. Sigma z is not there. Epsilon y is equal to 1 by E sigma y minus mu sigma x. Sigma z is not there. And epsilon xy is 1 plus mu. Here there will be 2 here. 2 into 1 plus mu by E into tau xy. This 2 is missing. So if we want to convert this in terms of stress or express stress in terms of strain, all we have to do is the last equation is simple. Tau xy, we write it in terms of strain. So it is just inverting the equation. As I said, 2 is missing here. So tau xy will be E by 2, 1 plus mu epsilon xy. But for the other two, you have to solve for sigma x and sigma y. Two equations, two unknowns. It's very simple. If you do that, you will see that sigma x comes out to be E by 1 minus mu square epsilon x plus mu epsilon y, and sigma y is equal to E by 1 minus mu square epsilon y plus mu epsilon x. Note that in the strain equation, it is negative here. Sigma x minus mu sigma y. Sigma y minus mu sigma x. But here, when you express this in terms of strain, then it becomes positive. Plus epsilon x plus mu sigma epsilon y. This comes out simply by simple algebra and solving two unknowns from two equations. This, if you do it, you will find it. It's very simple. So this is one example for plane stress. Now we'll go to plane strain. We'll look at another problem. The equation that we got from problem number 1, that is sigma x in terms of strain or stresses in terms of strain. So the problem is, using the results of problem 1, eliminate the stresses from plane stress equilibrium equation in the absence of body forces and develop expressions in terms of displacement. So what we have to do is to, first thing is to write the equation of equilibrium for plane stress. If we go back a bit, you will see that the for plane stress, equation of equilibrium is equation F. And equation F, it is simple: del sigma x by del x plus del tau xy by del y plus capital X equal to 0, and del tau xy by del x plus del sigma y by del y plus capital Y equal to 0. So if we take this for the case where there is no body force, in the absence of body force, then this equation comes down to del sigma x by del x plus del tau xy by del y equal to 0, and del tau xy by del x plus del sigma y by del y equal to 0. And from problem 1, we have written stresses in terms of strain for plane stress condition, and that is sigma x equal to 1 e by 1 minus mu squared epsilon x plus mu epsilon y, and sigma y is equal to e by 1 minus mu squared epsilon y plus mu epsilon x, and tau xy equal to e by 2 1 plus mu epsilon xy. Now, if you put B into A, all you have to do is to differentiate sigma x in B, sigma x, sigma y, and tau xy in B, and write it in A. And that is not a very difficult thing. You can do that. Having done that, you will get an equation in terms of strain. Now, when you write the strain in terms of displacement, you will get an equation like this. This is a very simple equation. Let me remind you, this is known as a Laplacian operator, which is nothing but del by del x, del square by del x square plus del square by del y square plus del square by del z square. But in this case, obviously, we have got in 2 dimensions. So Laplacian operator comes down to del square by del x square plus del square by del y square. I think this we have seen before, and if not, I think you can understand it very well. And G is the shear modulus, and Laplacian U is plus this will be equal to 0. There is something missing here. This will be equal to 0. That is not shown here. Plus e by 2 1 minus mu del by del x del u by del x plus del v by del x equal to 0. Similarly, G Laplacian V plus e by 1 minus mu del by del y del u by del x plus del v by del y equal to 0. Is equal to 0 is missing here. Please note this. Okay. So this is the problem 2, which is again is not a very difficult one. All you have to do is to substitute sigma x from B into A, and then you get an equation in terms of strain, and then write the strain in terms of displacement, which will look like this. So this is a simple problem, and I hope you can do it yourself and satisfy yourself. I leave it to you. Let's go to plane strain problems. Now, plane strain again is an assumption where we assume that the displacement field is reduced to u and v only. U as a function of x and y, v as a function of x or y, because it's a planar problem and w is not 0. And this means that for plane strain, we have got strain in z direction 0. Now, epsilon z, epsilon xz, epsilon yz equal to 0, and variation with respect to z is also 0. A typical application for this assumption would be a long bar, a prismatic bar, where the forces and traction and the body forces on the lateral boundaries are independent of z direction. That means whatever traction you apply in the lateral boundary are independent of z direction. That means you do not apply forces in the z direction. So that is the condition. And this is also true in many fluid mechanics and thermal problems, which you may have seen, that if it is a long bar, then the variation in z direction becomes negligible and it is neglected. So here again, the variation in z direction is taken to be 0, and strain in z direction is also 0. So in short, for plane strain, epsilon z, epsilon xz, epsilon yz are 0. And any variation of the strain with respect to z is also 0. So with this condition, we proceed and see how it affects our other main equations. So let's first look at the Hooke's law. In Hooke's law, we have got epsilon x equal to 1 by E sigma x minus mu sigma y minus mu sigma z. Again, please remember that epsilon z 0 does not mean that sigma z is 0. Okay? So sigma z will be here. So epsilon x is 1 by E sigma z, sigma x minus mu sigma y minus mu sigma z. And epsilon y will be 1 by E sigma y minus mu sigma x minus mu sigma z. And epsilon z equal to 0. That means 1 by E sigma z minus mu sigma x minus mu sigma y equal to 0. This means sigma z exists, and it will be sigma z equal to mu sigma x. It will be sigma x plus sigma y, not minus, because this equal to 0 means it will be mu sigma x plus sigma y. Okay, let's make this correction. And epsilon xy is g tau xy by g. So it is 2 1 plus mu by g by E tau xy. This is a simple one that we all know. And epsilon xz and epsilon yz are 0. That is the assumed condition for plane strain. Now, this we can again, like the previous problem, we can invert it, or we can write the stresses in terms of strain, because the last equation is simple to write. All you do, write tau xy is equal to g epsilon xy, but tau xz and tau yz are equal to 0. But to write the other three equations, you have to look at the first three strain equations, and there are three unknowns and three equations, so they can easily be found out with simple algebraic manipulation, and we get sigma x equal to lambda epsilon x plus epsilon y plus 2g epsilon x, and sigma y is equal to lambda epsilon x plus epsilon, this will be epsilon x plus epsilon y plus 2g epsilon y. And then sigma z will be equal to, in fact, the first term is same for all. Sigma z is equal to lambda epsilon x plus epsilon y is equal to nu sigma x plus sigma y. Because we have converted this into, there will be a g here, because there will be e here, because we have to convert this into strain. So this this term is to convert the strains into stresses, which this part is probably not needed. All we need to do is to write down sigma z is equal to lambda epsilon x plus epsilon y. Okay, and tau xy equal to g epsilon xy, tau xz, and tau yz are 0. Now here, lambda, if you do this simple algebraic manipulation, you will find out that the lambda is equal to nu e by 1 plus nu into 1 minus 2 nu. This is a constant that comes out in the algebraic manipulation. Nothing great in it. So we write this in terms of lambda. And then G is simply the shear modulus. So all this is simply written in terms of sigma x, sigma y, and sigma z, instead of epsilon x, epsilon y, and epsilon z. So now we go to next set of equation, that is the equilibrium equation. Again, the equilibrium equation for 3D I have written on the right hand side, and on the left hand side this becomes simple two equations, same as the plane stress, del sigma x by del x plus del tau xy by del y plus x, capital X equal to 0, del tau xy by del x plus del sigma y by del y plus capital Y equal to 0. If you apply the plane strain conditions, you will get this, because here, because epsilon xz and epsilon yz are 0, tau xy, xz and tau yz are also 0. So these two terms will be 0, and the last equation also will be 0. So we are left with only two equations and a simple form. Then we can go to the compatibility equation. I have given the compatibility equation in the full form, the sixth compatibility equation on the right hand side. And if you apply the plane strain condition, that is epsilon z, epsilon xz, epsilon yz equal to 0, you will find out only the top equation is left and other things are automatically satisfied. So you see, in plane strain condition, we have got simpler equations to solve and things become much simpler because we have assumed that it's a long component with a long prismatic component where the uh, uh, variation of strain in the z direction is 0. So we take a very simple problem here. The problem is like this. In the absence of body force, show that the following stresses satisfy the equilibrium equation in plane strain state. And it is sigma x equal to kxy, sigma y is equal to kx, and tau xy is equal to half ky square. It's very simple. All you have to do is to take the equilibrium equation, which is del sigma x by del x, del tau x y by del y is equal to 0. If you differentiate sigma x with respect to x, you get ky. And if you differentiate sigma y, tau xy with respect to y, you get minus ky. So that becomes 0. So the first equation is satisfied. Second equation is del tau xy by del x plus del sigma y by del y is equal to 0. That is the equilibrium equation. Now let's differentiate this tau xy with respect to x. We get 0 because there is no x term there. And then sigma y with differentiate with respect to y, and that is also 0. So it becomes 0. So both the equations are satisfied, and we can say that the statement is true. Okay, so that's it for today. We'll look at other things later.